get started, even though the field is also attractive, of course. It's a pleasure for me to introduce today's speaker, Professor Sasha Dmitriev from University of Gothenburg. Sasha, he did his undergraduate studies in Rostock, and then he did his PhD at EPFL, and was also at the Max Planck in Stuttgart. And then he moved to Chalmers in Gothenburg, where he was young faculty. Later he joined also the University of Gothenburg, where he's now a full professor. And during those the recent years, he was also on a longer sabbatical in the group of Mark Bronkesma at Stanford University. So I don't know how to describe your field, but Sasha comes with a background in condensed matter physics and experimental studies of surfaces, STM work, etc. Now he's doing plasmonics. If I should just say very quickly, we of course learned from our optics books that magnetism is never playing a role at optical frequencies. I think you will today at least see some attempts of magneto optics effects being enhanced if you go to nanoscale structures, and we're looking very much forward to that session.
Yes, thank you very much, Alexandre, for inviting me here in the first place, and thank you all of you to show up here for this talk. And I was warned that not necessarily everyone has the background in sort of nano-optics, and so I'll try to take it easy, and whenever it will be a little bit heavier, I'll try to stay on those slides a little bit longer and try to sort of explain that in a more simple and relaxed way. So don't be scared of whatever is coming. So as Asger mentioned, we try to do something with light, and that is happening at the nanoscale. And also we try to bring in the magnetism. And of course, like Asger also mentioned, fundamentally magnetism and light are not really keen on interacting. Light is extremely high frequency, and magnetism is at best 4 orders of magnitude slower. So how do you bring that all together? First, I would like to acknowledge the people who are contributing over the past 10 years, 15 years to these projects, and some have already left my group in different places in the world now. We have also keep on going, collaborating with Chalmers, University of Technology, which is also in Gothenburg, and also our long-term collaborators in Nanogun in San Sebastian. Recently in Linköping University, is a Swedish university, and in Belgium, in IMEC and École Polytechnique in France. And there will be different aspects of the science of light at the nanoscale that I'll feature, and actually these different collaborations bring different flavors into these aspects, like magnetism, sometimes solar actually. So we do a fair deal of working with solar light and trying to also couple it to nanostructures and see, well, where magnetism would come there eventually. Maybe that'll be at the end. But first, let's think about the grand challenge. And as we formulated recently, the grand challenge might be that we want a reconfigurable optics. And you of course know the human eye is able to refocus, and wherever you look at, you can do that in milliseconds. To refocus and actively change your lens to adapt to the environment. Unfortunately, the standard optical equipment cannot do that, because you have fixed lenses, you have fixed polarizers, you have all these components that once they're manufactured, they're fixed in their function, and to add extra functions, you either need to replace these components or start fiddling with your optical setup and combine them in different ways. So what Nature is doing sort of seamlessly, and every one of you is doing every single second, in optics is still not very accessible. So the idea would be, why not to have some sort of surfaces, and of course they will be covered with some sort of small structures that would interact with light. It so happens that the wavelength of, let's say, visible light is 600 nanometers, so you would imagine these kind of structures that interact with light maybe at that scale, maybe smaller, so in some nanoscale range. And if you would imagine the functionality that could be changed in real time, let's say you can change the polarization, you can change the phase, you can change the intensity or the propagation direction. That would be really interesting. So whatever you send in could still be reconfigured, and the function of your element could be changed in time, either fast or sort of in a static way. But if you would ask me, why would that be important technologically? But of course we know that even the recent examples of this mobile technology and the cameras that enter, you actually have to use two cameras to focus on the landscape. Sort of the panoramic picture and the portrait just requires different type of lensing. And of course, if you would think that instead of two, we are just using one camera, and the lens that would be sitting in front of that camera would be adaptable and changeable in real time, that would, of course, save in space, save in weight, save in whatever enters into the price of that phone, even though design of that phone probably enters majorly in the price. But still, technologically, even at this current stage, we would actually want to have some even simple lenses that are tunable and are still that could be integrated into the entire circuitry of that. Then, of course, we are staying in that paradigm of Cupertino and Silicon Valley. So what about the smart augmented reality devices? Again, you would like projection optics working dynamically. I mean, what augmented reality does, it just sort of what the smart glasses add to your vision is sort of the extra features of extra information that you could dynamically project on your vision screen that is basically positioned right next to your eyes. And again, these things are static, or it's a little bit of a cumbersome mechanics that is involved to sort of make that dynamic. So instead of, again, the same principle would work. If you have the screen and the light source, and in between there will be some element that is able to, say, steer light dynamically with the video frequency. So you would have like a moving pictures, and also so it could refocus differently, maybe produce some holographic projections at some viewing angles, things like this. So even staying within this sort of personal devices paradigm, we already see that the need for tunable optics might be pretty high. Finally, staying with this sort of the concept of Apple products. Of course, the LiDAR technology, the light detection and ranging, is now exploding technologically. All the self-driving capabilities of the vehicles need to be supported by these kind of LiDAR systems that just essentially sends out the light and detects it back. And you need to do that in three-dimensional space so that the vehicle or any other object can map the three-dimensional surrounding. And again, the necessity of having the beam steering, the necessity of having the tunable elements that can dynamically change how you send out the light, how you focus light, how you process the light back. Again, we see directly that there is a need for dynamical optical elements. And while right now it is made sort of on the mechanical basis, you have some rotating, like the whole scanning is basically done mechanically. Wouldn't it be nice to have a single piece of glass with some layer which is barely 100 nanometers thin, with some functional antennas that could be changed in real time, and thus the function of that surface will be changed, and hopefully everything could be integrated in a smart way into the cameras or the glasses, or maybe in the LiDAR system. So this is our starting thought. We should have something dynamically tunable that works hopefully in the visible, in the optical range. So it works with the light that we can see. We see the light from about 450 nanometers up to 780 nanometers. In that range, I just here tried to list some of the examples of how the tunable capability can enter. I do not say that this is the complete list, or there are many more groups working on that. I just try to out of my head to list whatever functionalities, for example, would be allowing this durability, the reconfigurability of your optics. You can do it thermally, you can do it magnetic-mechanically. You apply magnetic field, something mechanical is moving, you're changing the focal distance, things like this. Do it electromechanically, so you can again apply electric current, and maybe with the piezoelectric effect you can change the distance between the elements, the way they couple, things like this. You can do all optical, so you can by ultra short pulses you can induce nonlinear effects, and that would change the optical response of the system. You can do it by phase change materials, also a pretty popular avenue to reach the reconfigurable optics. And phase change means you experience the phase transition in some material, you say thermally activated, and let's say transit from the electric to metal, and then of course that sort of reshuffles the entire optical response of the system. It works pretty efficiently. So there are a number of groups working with that. There's Geroldev in Southampton, Capasso in Harvard, Farron in Caltech, Naliu in Heidelberg, Thomas Taubner, Niklas Kotter, Haldgiesen in Stuttgart. I will make more comment on the later work from Hal, because they actually also tried magnetic tunability. It also, out of the recent literature, I've seen some examples of the tunable optics. So just for you visually how it works, you have a surface, let's say, with the nanoparticles made of gold, and of course these nanoparticles, they support the so-called localized surface plasma. So the plasmas are just collective oscillations of electrons in these particles. There are a lot of free electrons in these particles. Thus they oscillate, and they are able to couple to light. And actually this is one of the reasons why stained windows work, for example. So small particles of silver or gold can scatter selective wavelength, can absorb selective wavelength, and that's why you can see these vivid colors that never fade, because also the particles are embedded into the dielectric matrix of the glass that we did in the Middle Ages. So the idea is that these particles readily work with light. They're in the size of some nanometers, maybe 50 nanometers, and the way they couple to each other also influences the way they interact with light. And in this particular case, they are assembled at the interface of the two electrolytes. One is organic, another one is aqueous electrolyte, and applying the different potentials to that interface, they either form a continuous film or they just randomly distributed in one of the electrolytes. And the consequences of that is that you can actually form a dynamic mirror. So if you have something under that container with the solvents, that was the 10-pound bill. So they're from Imperial College, yeah. So that's these are pounds. So you can see it through when the window state is activated. So it's this one. When the particles are just floating around, you see a slightly reddish color. I think that is the native scattering, somewhere in the red. And then you can apply that potential. You essentially reverse the potential, and then you form a mirror. And then so the coin is actually positioned above that container, and instead of seeing what's on the bottom, you're seeing what's on top. So you have a dynamic capability of a switching mirror. Of course, it's the liquid interface. I mean, technologically it might be a little bit cumbersome to integrate with electronics, but this is a very, very cool example of how in a reasonably simple means you can actually create a tunable optical element. It's a tunable mirror. Either it's fully transparent or it is reflective. Then of course the example from here, from SDU, Asger is the prominent figure in the field of changing, sort of writing down different colors, and then again you dynamically change the way these resonances interact with light, and you can create the entire gamma of colors, and potentially also could be maybe dynamically steered and reversible. So you can think of sort of reflective screens, things like this. So that is also one of the ways to create a dynamic surfaces that interact with the visible light. One of the very recent examples is actually the work from the group where I spent my sabbatical at Stanford, Mark Bomersma. And in this case, it's actually not even plasmonic, so there are no metals there. So it's the silicon nanowires positioned in front of the aluminum mirror. And just by tuning into different resonances, there are different kind of resonances, electrical, magnetic, at the different heights. So they build, Aaron is the first author of that paper, he built this MEMS sort of frame that is able, by applying magnetic field, it actually slightly bends. So essentially your wire is walking up and down. Well, the spacing there is like half a micron to the mirror, and then it moves, let's say, 100 nanometers by applying different voltages, but that amazingly changes the color of that wire. So you already have electrically tunable color of the scatterer of the visible light. It is not extremely fast, so you can probably do it best in megahertz, because then it enters into the resonance of the entire frame. So it's a little bit slow, but it's extremely functional. I mean, it's the visible change is amazing. You go from red to green, so you span the entire visible range. So these are some examples of how people tried in that field come to the tunable optical elements of different kinds. Of course, these are very simple functionalities, changing the color, changing the scattering, changing the transparency, but that's the first step. So I promised to talk more about Harald Gissen's work, and what they do, they actually combine plasmonic antennas that are gold antennas with the magneto-optical films. So then I will show you later how that potentially works, but even the simple combination of this kind of structures sitting on top of the magnetic film, which by itself could be magnetized, kind of creates already the functionality that we're looking at for. It's the functionality of changing, say, the circular polarization of outcoming light. So let's see how that would potentially work. Luckily for us, the essence of this combination of ferromagnetic elements or films and plasmonic gold nanostructures, nanoantennas, was kind of figured by Michael Faraday already 150 years ago. Even though he didn't combine them, he just discovered both fields separately. So first he discovered the magneto-optics. Magneto-optics is about applying magnetic field to some material, transparent material, how it's pictured here in his original figure. It's the action of magnets on light. So you send in the light beam through that material, and then you apply magnetic field to it, and it turns out that the polarization of the light that you send in starts to rotate or start to become elliptical. So you remove the magnetic field, it becomes linear again as the original, the incoming polarization of light. And that is the magneto-optical effect, which is called the Faraday effect in transmittance, and is also called Kerr effect in reflectance. So material needs to be magnetic, and material needs to be, well, reasonably transparent to reach that functionality. Well, at the same time, Michael Faraday was experimenting with the gold particles. I don't think he knew exactly that they were gold nanoparticles. There was no way to see them, but it's pretty amazing that the vial that he fabricated, so this red color, comes exactly from those localized resonances in the gold nanostructures that we've seen previously in the examples of this tunable optics. So he made those solutions of the gold particles, and this is exactly how your stained window would work. And this solution stays exactly the same through the years. And the thing is that you cannot really open that, because you would destroy possibly you would destroy the chemical composition of that solution. And so there is no real way to know what is the structure of these particles that he made by some sort of chemical synthesis, I guess, some sort of, I'm not sure how he actually fabricated them, but the colors have not faded for over 150 years while staying in solution. So they're not even embedded into any glass like your stained window would work. So he knew some secret there in plasmonics. He didn't know that it's plasmonics, but still it's quite a visual observation that gold does not look goldish anymore once you chop it into small pieces. It starts looking red.
So you can still go somewhere and see this bottle?
I think it's in somewhere in London, somewhere in the, I don't know, yeah, because that's a real photograph. Yeah, I should probably figure where we have these items in plasmonics that everyone needs to see. There is a cup that the Romans made based on this the nanoparticles that scatter and reflect different colors. So then you look at it with the light on the background, you see one color, and you look at it in reflectance. Just with the ambient light, it's different colors. It's green and red. And people in plasmonics tend to go to, it's in the British Museum, so people in plasmonics tend to go and at least take a picture there. It's a very small cup. So I think we should start a new tradition of people in plasmonics going find this bottle of Michael Faraday. Anyway, this is essentially how the magneto-optics works. If you have a magnetic structure and you apply a magnetic field, you can apply it in different ways. It's just one chosen configuration. It's called the longitudinal magneto-optical Kerr effect. So Kerr, I mentioned, it's in reflectance. Faraday would be in transmittance. And you have a regional polarization of light that hits that. It could be either a film, it could be nanostructures. So we like nanostructures. We started making nanostructures out of the ferromagnets. But essentially people also work with films. And once you send in the light and you reflect that light, the original polarization would slightly tilt from the incoming polarization, and that difference would actually signal how much the material is magnetized. And essentially that's how the Kerr and Faraday effects were used throughout the years, is to measure how the material is magnetized. If you apply the magnetic field, it's actually really nice to know how it is magnetized. And you can do that by magnetometry, but you can do it also optically. And it's sort of a non-destructive method because you just send in the light and you measure the reflected light, and then you know how your nanostructure is magnetized. And this, of course, is relevant for magnetic storage technology and in a lot of different technological applications. So this method was used throughout the years just to characterize the magnetic materials. The reason for why is that actually doing that, why does it rotate the polarization, is just that if you have a material which the electric function looks something like that, so it actually has the non-zero, non-diagonal element. So the plasma resonances would exist here at the diagonal elements. Changing them would change that color, all these plasmonic effects. But so here enters the magnetic field. So you're actually working not with the diagonal elements of your electric function, but rather with the non-diagonal elements. And here, depending on how you apply that magnetic field, X, Y, Z, you activate different elements, and you would bend light in different way, or you make it more or less elliptical. So then it's up to you to choose which configuration you're measuring in. It's basically, well, it's sort of a technicality. How do you want to probe your magnetization? The thing is that, of course, you could do nanostructures out of these ferromagnets that's what we're doing. And when you measure something like that, you can ramp your magnetic field. So how do you measure how the material is magnetized? You want to measure that response at each applied magnetic field and see when it saturates, so it's fully magnetized. No matter how more you apply magnetic field, it doesn't get more magnetized because all the spins are aligned, all the domains are aligned. This is what you can extract from this kind of hysteresis curves. So you start with a zero magnetic field, you start applying it, let's say in this configuration, and then you just interpret the polarization rotation of your light or the ellipticity of your light in terms of the smoke intensity. In principle, you could also just normalize it to the saturation values. Important is how the loop looks like and where it saturates. So you see that you start magnetizing your material, it goes up, and at a certain point it will stay magnetized no matter how strong field you're applying. And this is the field that you're applying, 500 Ørsted, and I promised the fridge magnets. So actually the fridge magnets that you have possibly in your kitchen are about 100 Ørsted. So it's 10 milli Tesla if you want to convert that. This is potency. So if you imagine that 100 is somewhere here, for certain structures you are pretty much at the fridge magnet limit. So it's a really low magnetic field. I mean, of course, these days you have this enormously strong magnets, even sort of the static magnets that you can use in your household can be pretty strong, but these are not necessarily those, so this is just the typical low fields that you get from the standard alloys that are on the market. So you don't need much magnetic field. If your structures are supposed to magnetize, so they kind of like to magnetize with a low magnetic field and all the domains are aligned, you don't need to apply a high magnetic field. But then back to the interpretation of that loop is that you can actually see quite a lot of features just measuring that, the rotation of polarization. For example, for these disks, you actually see the narrowing here in the middle, and that signals that your magnetization from originally in plane starts to curl upwards and form this like a vortex state. And at some point it gets stabilized, but then it decays. You continue applying magnetic field, and it kind of goes into your in plane position. So that narrowing actually signals that. Or here you would see that applying magnetic field along the different axes, I mentioned the easy axis, like where the material likes to be magnetized. It turns out that if you have an isotropic structure like the ellipse, you apply the magnetic field along the long axis, and you see that it actually keeps the magnetization even if you completely remove the field. This is how the magnetic memory works. You magnetize something, you need to remove that magnet, and the information stays there. So that is the nice way to store your information when you magnetize something along the so-called easy magnetization axis. Whereas in the short axis, there is no width of that loop. So you actually do not maintain the written information. And so you see actually here for the disks, you reach the saturation at much higher magnetic fields, but just because you a little bit helped the magnetic field with the shape of your nanostructures, you can saturate them at much lower fields, and well, potentially that is good for your magnetic memory. This is a short intro into how magnetoptics really serves the humanity to measure the magnetization of your structures and eventually the function of your hard drive.
Sorry, I have a very naive question here.
Sure.
I was all the way through thinking about how could you manipulate your off-diagonal elements here. How can you manipulate them? That would be interesting. And of course you do it by the magnetic field. But it seems by what you say here is either not or fully saturated. So if you would you have any interest in sort of scaling the saturation point? Can you do that? Is that, like I said, it's a naive question, probably stupid.
No, there are no such thing as stupid questions. We will know that. If you mean the level of the rotation
Yes.
that you produce, of course that depends on the material, it depends on the structure, because here you see it's one. There's just...
It's a normalization.
It's a normalization, exactly, yeah. So that actually happens at different, so you can actually rotate the original polarization of light more or less depending on the material that you use and depending on the structure. And actually I will show you later how we can play with that. So surely, I mean, all these intermediate points exist. This is real polarization rotation with the applied magnetic field. But certainly you would like to be somewhere here, because that's a static situation, so nothing is changing anymore. A slight variation of the magnetic field here will produce quite a substantial change in the polarization rotation. Like if you're sitting here, a slight couple of earthstats would create a big difference, and you don't want that for your functional system. But since I mentioned the nanostructures, and since I mentioned that we like them so much, I can briefly tell you how we make them. So it so happens that back in Gothenburg, where I work, we have a tradition of developing bottom-up nanofabrication methods. And bottom-up means we let the nature do the job by itself. So when we fabricate something, we just allow the structures to assemble in a particular pattern that is governed by electrostatic forces, interaction with the substrate, so there are different parameters that enter that. And then we use that as a mask to create all sorts of nanostructures. So what you see here are gold nanodiscs. And of course we do not deposit gold nanodiscs on the substrate. We use colloidal particles, and then with this series of processes, if you're interested, you can look at the details here. The paper been published 10 years ago. And it's quite a detailed recipe is given there in how you can produce various types of structures. So the thing with that is that you can actually produce centimeter square substrates in the matter of hour, maybe, different configurations of your nanostructures of different materials. So it's a really easy and cheap method of either making directly your functional nanostructures or just testing things. Essentially, you don't even need the clean room for that, because it's really like a wet bench process. You have aqueous solutions of the colloidal particles, and you need some instruments, to deposit metals, of course, or also to spin coat, the resist, things like this. But there's nothing compared to e-beam lithography or all this top-down fabrication where you really need an expensive environments and instruments. And it seems like that method had been picked up in several groups throughout the world, and the different structures that could be made. I mean, the library is pretty extensive. You can make dimers, quadrimers, different antenna, different sized antennas. You can make split-ring resonators. This is work from Harold Giesen. This is work from Naomi Halle's group in Rice. This is our own work where we actually made contacts for spin torque oscillators. So there's nothing even connected to sort of light and nano. This is a purely nanofabrication exploration of how how this method could be applied to make functional spintronic devices. So if you're interested in further details, again, look at this original paper. It's well described there. And it's not only to make nanostructures on a given substrate, you can also pattern your substrate with the features that you want to achieve. These are the examples of patterning polycrystalline silicon or crystalline silicon with the extra arrays of little holes in this case. And of course you add sort of a light management capability here. So you add like a photonic management to your solar cell. If your original surface is flat, you add these holes, they capture light better, you eventually increase the efficiency of the solar cell. In this case, that is the polycrystalline silicon solar cell. Here we actually enhanced quite a lot the efficiency here. The problem was that it's really hard to then put the top electrode on that structure because it becomes really, really porous. But the functional solar cell that is actually only effectively 600 nanometers thick with the efficiency of 8.6, that is independently confirmed, or I think the largest was 9 point something. So you actually have semi-transparent crystalline solar cells, and just because we patterned them with these little holes on top, it looks something like that. And we etch the solar cell. This is the thickness of the original solar cell. We essentially remove 50% of that material, and yet it is a reasonably high efficiency cell. So typically you would have 200 microns, and you would have an efficiency of 22% or something. So here with the sub-micron effective thickness, we are losing the efficiency only twice. Let's say. But this is just to demonstrate that the method could be used in completely different contexts if you are thinking of applying it to your own research. It's also that we were thinking that, of course, when you make structures, you would like to transfer them sometimes. Some substrates are not suitable to be patterned. Substrates like plastics, you cannot etch them. Substrates like money bills are pretty fragile. So, and if you want to add the extra nano functionality to these surfaces, we developed these special methods how to transfer the structures that originally you would make on, let's say, silicon wafer, well-controlled conditions. It doesn't have to be actually these bottom-up structures. It can be anything. It can be E-beam pattern that you want to put on this desk. Just transfer that. So we have something for you. It's a simple procedure that is again described in detail in this paper. You essentially use the sacrificial layer and you lift your structure and then you deposit it and then you remove the carrying film, and here you go. You can basically pattern PDMS fluidics. You can pattern glass, of course. You can pattern. This is the transmission electron microscope grids, where the supporting film, which is carbon, just carries your structures, and you can do analysis at single with the atomic resolution. You can wrap stuff with these carpets of nanostructures. Here they are actually supported by the film that is not visible in the electron microscope, but you see they're kind of, the carpet wraps the bigger spheres. The bigger spheres are polystyrene of 2 microns diameter. So it's pretty flexible approach that you could use. Again, you can deposit your structure. You see the pink color. So the pink color is the color of plasmonics. We've learned that in the first mirror. We've seen that in color printing. So these are the colors that are created by these gold nanostructures. And you can see that you can actually deposit them on pretty fragile objects and in pretty porous objects. And also you can deposit them on pretty low quality and cheap objects like a plastic of your commercial LED. And then you can even project whatever you deposited onto the wall here. No Photoshop, that's just the picture. And you see it's the logo of Chalmers University of Technology. It is projected from the size of like 50 microns here into the wall into 5 centimeters scale. So actually, that is of course written with E-beam lithography, but the pattern survives, could be transferred to really nasty substrates, really rough substrates, and it can even function like a projection mask. So now now we know how to make these things. Let's see what can we do combining magnetism and plasmonics. So essentially you want your magnetic structure be simultaneously plasmonic structure. That's the that's the key idea of the rest of the presentation. Of course, these localized plasmons can also come in the flavor of the propagating plasmon. So you have a film where these collective oscillations actually propagate along the interface. There's a lot of work done on that here at SDU. If you're interested, please talk to Sergey Bozevolny and Alexandre. But the concept of combining magnetism and plasmonics works surprisingly similar for these two types of electronic oscillations. You essentially want to change, for the propagating plasmons, you essentially change the K vector of that plasmon. For the localized plasmon, you really change how the near field looks like. The near field is something how the electromagnetic field gets confined to the nanoscale from the original field of light that lands on these antennas. There are several examples of how people combine that over the years. You can, for example, change the transparency of this kind of array where there are holes. So here is gold, and here is the magneto-optical active film. So when you measure the transparency and you apply magnetic field, the transparency is actually changing depending on which field you're applying. Here in millitesla, you already learned fridge magnet, 10 millitesla, good scaling, here 40. So again, applying moderately quite low magnetic fields, you can play with the transmittance in this kind of arrays. You can, similar to this example, you can actually change how the propagating plasmons react when you have a little fraction of your ferromagnet in the film. Or you can have this kind of crystals where there is this plasmonic antennas spaced equally, and then actually you can increase the magneto-optical effect of the underlying film. So in localized case, I will focus on the localized plasmons, the simple and visual example. It's where you have these discs that you've seen before. Now they're made of ferromagnet, this is nickel. And then you see that you actually have these resonances in the visible range that look like dipoles. So they actually support these localized surface plasmons. Localized surface plasmons, these are essentially dipolar oscillations in this case. You can look at the phase of this oscillation. So they look just like plasmons in your gold nanostructures, except now this is a ferromagnet. And the consequences of that, it's a ferromagnet, of course, we can make these loops, as you've seen before. We can apply a magnetic field, we can measure depolarization rotation, except that now depolarization rotation looks really different depending on whether you're sitting to the left or to the right of your plasma resonance. So you have this extra parameter all of a sudden in the system, this plasmonic response of your antenna. It's not just ferromagnetic anymore. You have this extra thing in your system that actually makes the magneto-optical response totally unpredictable from first sight. So you can actually change that on the fly. The thing is that what we were doing also, you can measure that in spectrally. So you can collect these loops at every single wavelength. So this dot, the height of that data point, is actually the difference between this saturation point and this saturation point, except that here they are normalized. But like I mentioned, they actually have a different height. All these loops have different height, means the rotation of polarization is different in all the systems, and that is actually expressed here. So K rotation is different at different wavelength. It's interesting that when we mess up the system here, is that when we add a little bit of the refractive index, the difference to our plasmonic antennas. And plasmonics actually is known to be sensitive to the surrounding index. This is how plasmon sensors are working. You add the molecules, and then your resonance feels the presence of that molecule just by the fact that the refractive index is changed around that plasmon resonance. So here, exactly that's what we're doing. We're changing the refractive index, and the whole thing is actually moving to the red. The actual consequence of that, if you're interested in plasmonic sensing, of course you can look around in the literature. I think there's also activity here. On that subject, some recent report, recent review, or you can look at the book that we happen to gather together. But the thing is that when you start adding ferromagnets to this sensing, you all of a sudden, again, you have an extra parameter. It's not just the optical resonance, the peak of your plasmon, but it's also this magneto-optically induced phase shift in your antennas. And I changed my mind. I don't want to go into details here, but essentially, well, you would be looking at this moving of that point that crosses zero of the magneto-optical response, just as in this example here, you would be just tracking one point here. So you know that magneto-optics goes to zero, and it's at some point it happens in many materials. And just because there are also plasmons in these antennas, the point will be moving, and by looking at how much it moves, you can actually build a sensor based on measuring magneto-optical activity in your nanoantenna. That's the essence of that work. Here, I would say like that. Of course, you can combine these antennas in different configurations. Here we are working with a dimer. The funny part that you can actually sense the distance between these two particles in a dimer, just as a single antenna would sense the change in the dielectric environment of that antenna. When you have two antennas, they would sense each other. And the distance between them is an important information that you would like to track. For example, in the systems where you actually want to measure distances at this scale, 10 nanometers, 20 nanometers. And all you need to do is just to expose them to magnetic field and measure the reflected or transmitted light from that system. And you would track the polarization rotation in this case, and for every 10, 20, 30, 40 nanometers in that sensor, you would have a completely different polarization rotation. But this is how you know that, okay, in my system, let's say it's the mass of some molecules, of some proteins, whatever, you would actually get a direct information of how different parts are spaced from each other just because you have this dimer attached somewhere to your functional units, and just by applying the magnetic field and measuring that polarization rotation from the outside, you would directly measure the distances with pretty high accuracy. So we were just making a formal comparison with what if this would be just made of gold. And it turns out the quality of measurement with the magnetic system is about 2 orders of magnitude better than compared to gold system. I guess that's all you would need to know. Here is actually the real example how these loops look like when we don't normalize them one to another. So you see there are all sorts of different polarization rotations available in the system. These are, again, this is just a simple nanoellipsis. And you can see that depending on how you come with the original polarization of light, here green or red, or something in between, this is just a disk, so there are no axes, you form completely different amount of polarization rotation. So I mean, this is like a cheap way of creating the tunable optical system. You just apply magnetic field to a ferromagnetic antenna, and you actually get a different polarization rotation as the outcome. So that's your tunable, real-time tunable system. Sort of given by the nature of magneto-optics, of course, get enhanced because there are also plasmons in these antennas, but it's simply because magneto-optics is there. So you naturally get the sort of magnetically tunable antennas. I think I will not skip that. You can formalize it in the math. It's just one highlight here is that, of course, you can play with the geometry. You don't have to stick to a flat ellipsis. You can play with the different configurations of your axis, and of course, you would influence your plasmon resonances in these antennas, and as a result, you would influence your magneto-optical carrier response. Let's say here, there's a dramatic change just because we change different configurations of this antenna. Staying basically with the same amount of material, is just that the way we come with light, the way we configure this antenna creates a complete different set of polarization rotations that come up. But of course, this is like a cheap way of making a tunable surface because we are not using anything else than just the intrinsic magneto-optical activity of these that happen to be plasmonic antennas. There is a bit of a more smarter way to do that. Now we want to combine the gold, which is the classic plasmonic material, nice scattering antennas, with ferromagnetic elements, and see how that could influence whatever we can do in the near field, that is in the scale of nanometers, or in the far field, so the light that comes out. This is just a surface that is filled with these antennas. These are trimers. So when the trimer is made of purely gold nanodiscs, what we measure actually, it is symmetric. and what we measure is the difference between the transmission of the right and left circular polarized light. Okay, in chemistry it's called circular dichroism. Here is a little bit more complicated with the naming because, well, we better stick to differential transmitters, okay? And not to offend people in different areas of chiral plasmonics. We just measure the transmission without even analyzing its polarization state. So we send in the circularly polarized light to the left or right, so your polarization is just rotating clockwise or counterclockwise. And out come some photons that we just detect when we collect this spectra. So of course this is, I mean, here necessarily comes the concept of chirality, that you have the, you know, right and left hand cannot be superimposed. That's the last. Yeah. So the thing is that when you end adding the ferromagnetic elements, not only you break the symmetry, but you also get this dynamic tunability. And this is how you essentially get it. So if you look here, this is the schematics of what we're doing. There is a circularly polarized light that comes in, and then we apply a magnetic field to that surface. So gray here is the differential transmission from this surface when there is no magnetic field. And then you start applying plus or minus magnetic field, which is in this case out of plane, and then that is the tunability that you get. You essentially can reshuffle your response of your chiral surface, so it can be substantially more transmitting right circular polarized light, or substantially less transmitting right circular polarized means transmitting more left circular polarized light. You can play with the parameters of these antennas that luckily our method of fabrication allows that. You can change the gaps, and at the end you can map something that is the tunability, sort of how much can you tune that system, and it turns out that in certain configurations you can tune it up to more than 100%. So if you're sitting somewhere here, let's say, your original response is somewhere here, you can actually sort of change that more than 100% in terms of how much circularly polarized the light comes out. So this is, we see it as the starting of this adventure of tunable optics, while we're not using purely ferromagnetic structures, which are also actually pretty absorbing. So in this case, we start going into plasmonic metals, and the thing is that the whole concept also holds for high refractive index dielectric structures like silicon. So in principle, the same ideas would apply to basically fully transparent surfaces. How can you change the response of the surface by applying external magnetic field? So I would, this is not magnetically tunable yet, so I would skip that part and jump into the final slide. And of course the future, as I say, we see that system as the first step towards truly magnetically controlled optics. But also, why not to think of the chemistry? You know, when you have these things and you have a near field, and if you have photoactive molecules that probably transform under the influence of that field, wouldn't you be able to control the transformation of the phototransformation of the molecules just by applying externally magnetic field? So you would have like a magnetically controlled chemistry at the nanoscale. Then what we're trying to explore is the functionalities on the unexpected surfaces, such as these. And this is open. I mean, we create the method. It's open to everyone, for everyone to use, and I'm happy to assist. And I didn't mention this the solar thing, but then again, what if we can create the antennas that absorb the solar light, and the amount they absorb is tuned by the applied magnetic field? So it's sort of like magnetically controlled solar cells, magnetically controlled solar surfaces. But that's what's coming next. So thank you for your attention. I'm happy to answer questions.
Questions? I have
First, one question, maybe you mentioned it at some point, what's kind of the time scale for dynamic processes here? So we say,
Yeah.
for your technical example, I guess your iPhone should do this in
Yes.
realistic time, right?
Yeah, sure. I mean, magnetic field is of course not extremely fast.
Mhm.
And the fastest you can get, I think the commercial sources reach about 10 gigahertz,
Okay, but it's
changing up and down.
pretty fast.
That is
I mean,
pretty fast.
yeah.
That's already technologically fast enough to, I mean, it's beyond the video and all that. So it's like you can actually process the information.
So you can go kind of through this hysteresis curves, I guess. I mean, on
Yeah.
gigahertz time scale.
The gigahertz times, yeah. So I mean, there are right now there are sources of I think 10 gigahertz, or even 20 gigahertz. You know, I mentioned this tunable silicon antennas and all these, of course, thermal processes. That is really slow,
Yeah.
unfortunately. So all these transformations would happen, yeah, I don't know, kilohertz or megahertz at best. I mean, it's fundamentally limited. Here we are in a little bit better situation.
Does heating, is that a problem for you? Because, I mean, usually when you heat up, like magnetics gets worse and plasmonic antennas, they do heat up, right? I mean,
They do heat up, yes. So we do not use high intensity light sources.
Okay,
And we actually, they do indeed heat, and the fact is that we actually explore that for this solar thing, that they tend to absorb a very broad spectrum of light. So if you remember those resonances, they're pretty broad. So gold would be really sharp and it's absorbing at 500, nice color, whereas nickel and all these ferromagnets, they're fairly broad. So they're not that efficient absorbers, actually, at the given wavelength. So, but certainly yes, and of course magnetic properties decay with increased temperature. And yeah, we faced several of these difficulties when we combine, let's say, noble metal antennas that heat up extremely well, and then you have some ferromagnetic elements, and that is just completely baked when you just shine in a laser light, because the plasmas are so efficient in capturing light and transforming it into heat. It could be an issue, yes.
When you transfer your structures,
Yes.
is it with a substrate or without a substrate? For example, this picture you showed with
yeah.
the arrow there.
Yes. So I mentioned that briefly. So the supporting thing that makes them float is the carbon film. It's amorphous
Yeah.
carbon of 10 nanometers.
Yeah.
So you make your stuff on the amorphous carbon film, and under that carbon there is some area that could be removed by, let's say, etching.
Yes.
So thus they start floating. But then the carbon film, of course, is easily removed by a really brief oxygen plasma etch.
Yeah.
So it's enough to etch it like for 5 seconds, and the supporting carbon film is completely gone, even under the structure. So your structures land on your target substrate, because these guys are not supported by any carbon. These are the pristine gold nanodiscs that are sitting on the light bulb
Okay.
or on the bill.
Last question?
I was thinking when you showed how these electro-optical effects changes with wavelength,
Yes.
going across the plasma resonance.
Yeah.
I mean, what would, given that even the design of these electro-optical effects changes, it goes to the right at a certain point, while at another wavelength it goes towards the left.
Mhm.
What would happen if you have like a laser with the bandwidth as large as the resonance, and you see the reflected light of the laser? Because part of the wavelengths inside the laser would rotate left, and another part of the laser would rotate right.
Yeah, actually, the funny part that in principle magneto-optics is used to isolate your laser cavities.
Yeah?
Because when you apply a magnetic field, the system becomes non-reciprocal. So imagine you have a thick bulk of transparent magneto-optical
Yeah, it's the
material.
Faraday rotator principle.
Exactly, yeah. So you actually shine in the linear light, it rotates 45, but when it comes back, it rotates further 45 because it's non-reciprocal. So if you have a cross-polarized scheme, that light can never come back.
Mm-hmm.
So it actually is used in the lasers. But of course, in this case, the magneto-optical response need to be as flat as possible throughout the operation range, I would say, because of course we're twisting things. We're adding plasmons, it starts to be extremely wavelength dependent. But I mean, the nickel film, let's say, it is sort of reasonably flat as a material, as a magnet-optical material.
Yeah, but like in that case, it seems like you can create like an energy vortex. I mean, a vortex which is energy resolved at different energies, you have different polarization, and you have a point.
If you can have a sharp gradients in how the magnet-optical response looks like spectrally, surely, yeah. If you have a sort of spectrally separated, 5 nanometer spectrally separated lines that one would, you know, rotate 45 to the left and one would rotate 45 to the right. Yes, certainly, but it's actually quite hard to make those sharp gradients in magnet-optical response. Most of the materials have really flat, at least in the visible, really flat rotation or ellipticism.
In the interest of time, I suggest that we continue discussions offline. And, so let's thank Sasha.